Good afternoon, everyone. I am Jhansi Moida from Lengi Institute of Engineering and Technology. During my internship at Amatis Information Technologies, I developed an EV ADAS dashboard using STM32 Blueprint, PiximLab, and Python. Today, I will explain the project, its implementation, and the results. Real world motivation. Modern electric vehicles generate a large amount of real time data, making it difficult to monitor everything manually. Our solution is an EV ADAS dashboard that displays vehicle parameters, detects collisions and blind spots, generates alerts, and provides a live dashboard for better safety and monitoring. System System architecture. The system starts with sensors that provide input to the STM32 blueprint. The controller processes the data using EV control and ADAS algorithms and sends it through UART. The Python dashboard receives this data and displays speed, battery status, range, and safety information in real time. Industry versus our project. This slide compares our simulation with a real electric vehicle. Instead of expensive automotive sensors and can communication, we can use potentiometers, STM32 UR, and a Python dashboard to simulate the same concepts in a low-cost environment. Project roadmap. The project was completed in 9 phases, starting from software setup and peripheral configuration, followed by EV dynamics, ADAS implementation, call detection, UART communication, and finally a real-time Python dashboard. Environment setup and GPIO. We used STM32 Cube IDE for firmware development, PiximLab for simulation, and Python for visualization. Timers were configured for scheduling, ADC for sensor inputs, UART for communication, GPIO for LEDs, and PWM for the buzzer. ADC and EV dynamics. The EDC reads accelerator, brake, and motor temperature values. The EV Dynamics module uses these inputs to calculate vehicle speed, torque, battery state of charge, range, and regenerative braking based on the selected drive mode. Ultrasonic ADAS. Three ultrasonic sensors continuously monitor the front, left, and right sides of the vehicle. Based on obstacle distance, the system provides forward collision warning, blind spot detection, parking assistance, and time to collision calculations for improved safety. Fall detection. The system continuously checks for motor overheating, low battery, collision risk, sensor failures, and communication errors. Depending on the severity, it generates advisory, warning, or critical alarms that safely stop the vehicle when necessary. Your telemetry. The STM32 sends all vehicle and ADAS information to UART every 100 milliseconds. The transmitted data includes speed, battery charge, torque, temperature, obstacle distances, alarms, and fault status for real-time monitoring. UART shell. The UART shell allows us to test the system by entering commands such as changing speed, battery level, temperature, drive mode, and fault conditions. This helps validate the system without changing hardware inputs. Here is the Python dashboard. The Python dashboard receives your data and displays it using speedometer, battery indicator, speed graph, EV information panel, and bird's eye ADAS view. This provides a clear real-time visualization of vehicle status. Results. The project successfully demonstrated a real-time speed and battery monitoring, collision detection, blind spot detection, motor fault, handling, UART communication, and live dashboard visualization. The complete system worked successfully in the PiximLab simulation environment. Now I'll explain the All the QID initially common.h. This is the common header file used throughout the project. It includes all required libraries, utility macros, drive modules, and common definitions that are shared by every module. Next, EV control. This file defines the EV model. It stores vehicle parameters such as speed, torque, battery SOC, motor temperature, range, and regenerative braking. It also contains the functions that calculate the vehicle's behavior. Then, ultrasonic.h. This file contains the driver for the HC-SR04 ultrasonic sensors. It defines sensors IDs, distance limits, timing parameters, and functions to measure obstacle distances from the front, left, and right sensors. Then ADAS.h. This file implements the ADAS logic. It defines alarm levels, collision warning thresholds, blind spot detection limits, and time to collision values used to improve vehicle safety. Then fault.h. This file handles fault management. It detects conditions like motor overheating, low battery, and critical collisions, sets fault flags, and places the vehicle in a safe state required. Then UART shell.h. This file implements the UART command interface. It allows users to send commands such as changing speed, SOC, temperature, drive mode, and resetting faults for testing and debugging. Main.h. This is the main configuration header generated by STM32 cube IDE. It contains GPIO pin definitions, peripheral configurations, and project-wide hardware settings. Then ultrasonic.h. .c. The source file generates trigger pulses, measures echo pulse duration using timer 2, calculates the obstacle distance, and stores the measured values for the ADAS module. Overall, the project allows a modular design. This sensor driver collects input data. The EV control module calculates vehicle parameters. The ADAS module analyzes safety conditions. The fault model monitors system health. And finally, the UART module sends all processes data to the Python dashboard for real-time visualization. Now we go for project explanation. My project is an EV ADAS dashboard developed using STM32 F1003C8 Bluepill, PiximLab, and Python. The main objective is to simulate an electric vehicle and implement advanced driver assistance system features such as forward collision warning, blind spot detection, and parking assistance. The STM32 continuously reads inputs from simulator sensors like accelerator, brake, motor temperature, and ultrasonic sensors, processes this data using EV control and ADAS algorithms, detects faults or unsafe conditions, and sends real-time telemetry through UART. A Python dashboard receives this data and displays vehicle parameters such as speed, battery state of charge, torque, range, temperature, obstacle distances, alarms, and fault status, providing a complete real-time monitoring and safety system similar to that used in the modern vehicles. Now we look into the how this system works. Here is the potentiometer This is accelerator, brake pedal, SOC, and temperature. Here we have three ultrasonic sensors which measures front distance, right distance, and left distance. And the visual monitor where we can observe all these values. If we have temperature is very high, then we can observe that fault state is high. And here we have EV ADAS dashboard. How this works is if if we increase the temperature, if we increase the brake, then torque will give us negative values. This system is regenerative braking system, and we can observe here speedometer, battery charge, speed history, and EV metrics. In EV metrics, we are having torque, acceleration, brake, motor temperature, alarm, fault, and signal. And if the front distance is low, then our collision signal will be high and also detects fault signal. And here ADAS bird eye view where we can see our alarm critical conditions and how our vehicle is moving, and fault conditions 0x05. If the front distance is high, then we can observe that our collision signal is low and the vehicle is not at a proper alarm in safe zone, and vehicle is away from the another vehicle. If the brake pedal is less, we can observe that the torque is positive. Here we can observe that torque become in a positive value when the brake is low. Here we can observe the brake is 4%. And if we increase the brake value, then we can observe in the dashboard that torque will become in a negative value, which is the reverse regenerative braking system. Here we applied 99% of the brake, and we can observe the speed history here. And this is the entire overview of our EV ADAS dashboard system. Thank you.